can, so I guess the other microphone's working. So welcome. And this is, I always give talks. I'm a dangerous guy to invite to give talks because I give talks on things that people don't expect. So in 1991, I was situated between Dan Quayle and some presidential candidate, and I gave a talk on how you could get rid of all taxes. And within 100 years, there would be no more taxes because the government would print money. And I was laughed out of the room because the government will never print money because it will distort the economy and destroy itself. And of course, the government prints money. So with that, you can actually have no taxes. And of course, I got no applause, and I was basically run out of the room on a rail. So today I'm going to do another one of my talks, and I'm going to talk about something that everybody in this room can become a billionaire in 5 years on, and I'm not kidding. And so at the end of this thing, you're going to hear me give everybody a business plan that you can become a billionaire, and all you have to do is talk the drive guys into putting some firmware on the drives, okay? And we'll see how this works out. So the sort of takeaways for the talkers, this talk, I'm a personal storage device guy, not really a SAN or a storage systems guy. It's just I do both, but I like both, and you'll see this and so forth. But for me, it's PCs, pads, phones, cars, homes, businesses, et cetera, et cetera. So all that's personal. Businesses are personal. Business laptops are personal. Okay. One of the things I want to point out here is really self-encrypting drives are fantastically successful. I've been in many meetings in the last 5 years where people incorrectly think nobody uses self-encrypting drives. And I'll tell you how fantastically successful they've been. And I'm going to tell you about an initiative. So I went around the world in the last 4 months, and I bought every open source group for TCG self-encrypting drives. And we formed a Drive Trust Alliance on open source around TCG, Opal and Enterprise drives across platforms, Windows, Linux, Mac, and so forth and so on. And why we're doing it, and you'll see this. And then I'm going to mention two other, what I think of as really interesting open source projects. They happen to be out of MIT. So I'm from CMU, and I'm sure if there was a CMU person here, but the bottom line is they're out of the media lab essentially, and I want to show you what they are. And one of those two, a good friend of mine is the head of the Kerberos Consortium, and he and I have this scheme that if we get somebody to do it, they can make $1 billion, or they can become the next, Zuckerberg, whatever his name is. So I'm doing it again. So this is the sort of agenda, and it's kind of a cycle. So I'm going to talk a little bit about security evolution, where we are, what's going to be happening. I'm going to mention the Office of Personnel Management. Talk a little bit about security and privacy. I've been teaching security at Carnegie Mellon in School of Computer Science since 1996. I teach it every year, taught it this year. And so I have some views. And then I'm going to talk a little bit about SEDs and object storage, a little bit about the TCG core, which is the TCG spec, and I'm the author of the TCG spec. So I'm the original author of the core. It came out of my brain, and I'll tell you what we're really trying to do, just for fun. And then I'm going to talk about a personal data system, and that's how I'm going to show you how to make $1 billion. So I call today the sort of the age of uncontrolled data leakage. So we're in an age in the sort of security evolution of uncontrolled data leakage. It just leaks everywhere. And we're learning how to keep data under control again. We had it for a while, we've lost it. And my argument is that where it's uncontrolled is computer forensics, digital evidence. Eric mentioned them with him on the ABA committee. And I regard what some of those people do as uncontrolled data leakage. Corporate collections like Google, Yahoo, Microsoft are unsupervised data leakage mechanisms on private personal data, business data, you name it. Okay. There's a great thing that Snowden released. It's called the NSA ANT catalog. And if you haven't gone on Google and downloaded it, you should. Okay. Because that shows you the data leakages and how the NSA has been targeting. So there's like 41 products there. Each one of them does data pulling through the infrastructure, and each one's described in detail. It's not classified anymore because it was made public, and of course once you make it public once, it ain't classified. Okay. And so you can just download it. Of course, NSA is watching you download it, I am sure. Okay. But it's a great thing, and pass it around to all your friends and let them see that thing, because it's actually a wonderful catalog of ways to get at data. Ransomware out of Russia. We were at a meeting 6 months ago with the FBI and Secret Service, and they basically said, so ransomware is you're phished, you push a button, it starts encrypting all your data, you're then handed a notice and it says, please give us $5,000 and we'll decrypt the data and give you back your data. Okay. The ransomware has now become extremely sophisticated. And so you'll see on TV ads that they say that it's $5,000. It's not. If you're even a medium-sized company, it's $100,000 to get your data back. Okay. And it is cryptographically controlled, and there is no cracking. That, if there was a way to do it, we would know, undo it. But that's basically out of Russia. They make big business out of it. The Sony breach last about a year ago. Okay, and I've got references at the end of this talk, and it'll be up on the web where you can go see the best articles on all these things. The Sony South, which was within minutes, over 1,400 laptops and PCs within Sony were bricked, and Sony was brought to a halt. The corporation was brought to a halt, and they had to learn to do things on paper until they could get rid of what had happened. So Fortune magazine has a huge article describing all the details on this, and it's a great thing to read. The Office of Personnel Management, which I regard as one of the most significant attacks on a country in the last 100 years, the Office of Personnel Management for years and years has been keeping all the records on the process of going, the forms you have to fill out and the interviews that are done to give you secret clearance in the government. Okay, and so all that data was taken. Basically, all the data was taken. So I asked, my reaction when I first saw it was somebody needs to go to jail for a long time in the government. And I was just told Monday that nobody's going to go to jail. And I said, why isn't somebody going to go to jail? And y'all won't believe this. This is the data sets of all the information that, all of your lifetime, your brothers, your sisters, your mother, your father, your neighbors, their Social Security, every Social Security number all this information and how they're connected to you. Plus, on the NIST website, you'll see there's a categorization that's assigned to each person. The categorization says like analyst. It doesn't say spy directly, but it says like analyst. It says exactly what jobs you're suited for. Okay, and so the guy's got pre-categorized data on all the people with secret clearance and above in the United States, and all their friends and their families. Okay, and I said, somebody needs to go to jail over this. And so I was told that the legal profession's answer to that was, and y'all won't believe this, none of the material in the Office of Personnel Management was marked classified. So nobody goes to jail. This is unbelievable. Okay. So this is one of the worst things that's ever happened. Anyway, all this stuff is phishing initiated. So I'll argue that Google is phishing initiated. Google is just this big phishing machine that gets you to hit the return key. Okay, that's what it is. Okay, so everything is phishing initiated, and then somebody else gets paid or worse for your stuff, for stuff that's yours. Okay, and there, people will say, well, you're giving it up, voluntarily. Yeah. So here's sort of Security and Privacy 101. And to my students, I always say, in one sentence, what is security? Security is access control. That's the end of it. Okay, everything else falls out of that. Okay. And my argument is that security should serve up privacy. And so I've got so the classic notion of computer security is CIA, confidentiality, which means privacy, integrity, and availability. The way I teach it, it's IPAA, integrity, privacy, authentication, authorization, audit, and availability. And the first three, integrity, privacy, and authentication, are done with cryptography. And then authorization, audit, and availability are like table lookups or just writing, that's just code. Okay. And so you can actually figure out how computer security works by saying, well, the first three, I'll learn the cryptography behind integrity, privacy, and authentication, and then I'll just understand that these last three are really not cryptography. Okay. But they all are in service to privacy. They're all in service to the fundamental purpose of computer security, which is access control. So the original thing that I went to Seagate with back in 2002, 1, whenever it was, was this idea that a storage device is really a complicated system, CPU and so forth and so on. And what you do is you put a security subsystem in the storage device, and it controls access control on properties of the device itself. So for example, you've got diagnostic ports. It puts access control on diagnostic ports. You put probe ports, you put access control on that. You could put access control on firmware functions inside the device, access control on special hardware functions like encryption engines, put access control on the data sync and source, how stuff gets written to the disk and so forth and so on. And you get and then you just write a definition of a security subsystem that does all the access control inside of a drive, and you've got a really neat solution. So we did something called a core spec, and the core spec is fundamentally an answer to any question. So if what you want to do is you want to do not only data at rest protection, but you want to do data in transit protection, the core text gives you specs on how you do it. Okay. Now Opal and Enterprise don't implement that. The way the SSCs work is these are taken from the core spec, a subset of the core spec specification that are chosen for the purpose. In the case of Opal, it's laptops and so forth. Enterprise is enterprise self-encrypting drives. And but under any SSC that's defined by TCG, anybody who implements, like for example, an Opal SSC can take anything else out of the core, put it in their drive, and point to the core spec and say, we just implemented that part of the standard that's not required under Opal, it's just optional under Opal. So the core spec is worth looking at, and happy to sit down with anybody and tell them, and we've got another person who sort of half likes it in the back, who's sort of the head of the storage work group, Jason Cox, now from Intel. But one of the things to understand in the core spec was that when I originally designed it, it assumed there was a scripting engine inside the drive with really simple scripting. So that's never appeared. It appeared in the original Seagate drives. And is there a Seagate guy here? Good. Okay, so it appeared. So I put a scripting engine, for the first 7 years, there was a scripting engine in every drive, but we couldn't tell anybody about it. And we put Lisp into the drives. So we put a Lisp interpreter into the drives because all we needed was very brief, very simple scripting, so there was no garbage collection problem. We just needed it to implement different things like DRM and so forth using the core. Okay. So there's this notion of security providers, which are the components. So in that last slide, the security subsystem has different things that it can attend to. And so each of the things that it can sort of attend to are associated with something called a security provider. And I'll give you sort of the basic ones. Is the administrator, that's the super user for the security system, the admin SP. The locking SP, that's the self-encrypting part. So when you control the locking SP, you're managing the self-encryption in the drive. A clock SP, which to my knowledge has never been implemented, is a date and time. Obviously in security, if you're doing audits and so forth and so on, it's useful to have a clock, a real clock, not a timer. Okay. Forensic logging, so we defined a forensic logging SP that would automatically log and audit things that were going on inside the system as an audit log for security. Crypto services, so it had the full capability of being something called a Microsoft CSP or PKCS 11. Internal controls, and internal controls was the diagnostic ports, probe points, and so forth and so on. But that is the whole TCG spec in a minute or two. Okay. So I now run something called the Drive Trust Alliance. In a second, you'll hear a little bit more about it. But it has to do with me having bought all this open source guys. So I bought a bunch of. They work for me now. Okay, and so I hired them all. Okay, and now we have all the open source that I know of that's available in the world for TCG spec self-encrypting drives. So we get to define what we consider to be an SED, and since I'm the guy who did SEDs, I get to define it. And so it's a device built that uses built-in hardware encryption circuits to read and write data in and out of non-volatile storage. That's my definition. And then I have an additional piece of a definition that's actually not in the spec, but is part of all the drives that we know of, and so forth. There's at least one medium encryption, or media encryption key is protected by at least one key encryption key. So a key encryption key wraps or encrypts the media encryption key when the data is at rest. And so you cannot get to the media encryption key unless you know the key encryption key. And so I can take a self-encrypting drive. It's at rest right now, and there's no amount of engineering I can do to find the media encryption key off this drive. Period. Just not possible. Okay. And that now all of a sudden you've got a really interesting security model. So here's the landscape, and this is this success that people don't realize is a success. Okay. So the first thing is 100%, and there's some exceptions but not much, 100% of all the SSDs you can buy today that are new, not ones you could buy that have been sitting on Amazon's shelf for a year, but 100% today, 100% of Micron, 100% of SanDisk, 100% of Intel, 100% are self-encrypted. 100% of the SSDs. 100% of all enterprise storage. 100% of all enterprise storage, whether it is SATA, SAS, SSD or rotating media is all self-encrypting today. One of the companies that made that happen was Google. Well, there were two or three companies. One of the big ones was Google. Google has been 100% self-encrypting in the data centers since on the order of 2008. People don't realize this. The TCG enterprise spec was really successful. Okay, 100% of Amazon is. It goes on. The use case is really repurposing the drive. It's cryptographic erase. You change the media encryption key, which is a microsecond, okay? And now you can do with that drive whatever you want, and you're not losing anybody's data. Okay. So it's a wonderful mechanism, and it's used in enterprise all the time. One that most people don't know, so I knew Steve Jobs pretty well, and back in 2006, I tried to sell him on self-encrypting drives, okay? And he put into the iOS devices, all iOS devices, all phones, all pads are self-encrypting drives. And I explained to him the key encryption key, media encryption key. He called Seagate's salesperson in charge of Apple and told Seagate to deliver 2,000 drives to him that afternoon. I got a call from the Seagate sales guy, and he said, "You know Steve Jobs?" And I said, "Yes." And he said, "You talked to him?" And I said, "Yes." He said, "Do you know what he just did?" And I said, he said, "We weren't supposed to tell him about this stuff." And I said, "Okay." I'm a naughty boy. And but the result is that every iPhone and every iPad since day one is self-encrypting. So the password you give it on the front is actually the key encryption key, and it unlocks the hardware, the media encryption key. And so they give you the ability to do long passwords so that you can really set a good, strong way to protect the data. And then they partition the storage into user storage and system storage to keep the phone working. System storage is running the phone, so it still answers the phone and so forth. But while it's locked, okay, it's hardware data at rest for all the user data. And it's been this way since day one. Now Samsung Knox is this way now. So it's making its rounds in the phone world. The actual reason, if you talk to the Apple engineers, the reason that they do that is software encryption is so power intensive, you lose 40%, I'll give you an example, you lose 40% of the battery life on your phone if you're running BitLocker in software. 40% of the battery life. It has to be in hardware. So it has to be hardware self-encrypted. This is a success. There's a much smaller number of personal hard drives and SSDs and so forth that are Opal or SED, which is true, and that's what the Drive Trust Alliance is dealing with. But Microsoft BitLocker supports eDrive, Opal 2.0 drives of all kinds. And then Opal drives also supports, all Opal drives also support SATA security password, which is self-encrypting. So you don't even need software, you just bring up the BIOS and you can set the disk password, and you're doing exactly the same thing without any software on the machine. It's all pre-boot. And then NVMe and other personal storage devices are being handled by the TCG storage work group, and I'm sure Jason will tell you all about that later. So the Drive Trust Alliance, its fundamental purpose in life is to facilitate adoption of personal SEDs. That's its sole purpose. We've got the team that originally did the TCG stuff. We have the marketing lead who's on SNIA education here. He's giving a talk this afternoon on SED. And so what we're doing is we're going out, and it's a Red Hat story. We have this open source. We'll do customization on the open source for cars, houses, or whatever. We'll do marketing and whatever, education on the for other companies who are trying to increase adoption by the average guy out there on SED technologies. It's wildly successful, and people don't know that. And then we're asking for money, sponsorships, because we believe a rising tide lifts all ships. So all the drive makers can participate and so forth. So we announced this alliance at the Flash Summit, and we now, and so we have a little website you can see, and the full service of the website will be up October 15th. And we now have at this moment, y'all are the first to find out, we now have a full-blown sponsor. That's our first. So Micron has now joined the Drive Trust Alliance. So in terms of thinking ahead of the world and so forth, I have SP-SED, and when I say SP, I mean one of two things that's ambiguous. One is security privacy SEDs. So advanced SED technology, not the stuff that you just buy with an oval. Or it could be security provider SED. I don't know. It's whatever. SP stands for something. When we talk about cloud things, every personal device is now actually in the cloud. This is the truth. Okay. So what should you do with SSDs? What should you do with flash, PCIe flash? What should you do with hard drives? Okay. Look in the clouds for what should be in the personal storage device. You know, what should this thing be able to do all by itself in a self-protecting way, and look at what the cloud guys are doing and say, well, that should be in this. And that's a good rule. So that's kind of like a engineering architecture rule. It's a fun rule. So one of the things that we put in the TCG spec that makes it sort of unique is this idea of TCG, SEG ranges. So you can have essentially partitions on the storage device that each has its own key, each has its own unlock lock capability. And so you can put a certain number of partitions. So if you think about it, this guy has an open range, which is the system, the thing that's running the phone. Okay. And then it's got a locked range, which is the user data. And actually, every year, Apple, if y'all don't know the details of how Apple does their stuff, every year around January, they publish a very nice, beautiful paper on the security architecture underlying iOS, all these devices. It's typically 30 to 50 pages, and so every year they bring it up to date, and you can go just get it off the web, and it's a wonderful thing. TCG Enterprises, the ranges were originally intended for VMs and enterprise situations and so forth. There's a BitLocker eDrive uses 4 ranges. One of them's open. It's like the iPhone. The U.S. government they actually use this is not classified. It got declassified, I think, for the Drive Trust Alliance. That I can tell y'all that the U.S. government has been using our open source that's been around for 4 or 5 years that I happen to have bought now, for creating what are called resilient PCs using ranges. So the open source is in use. It is out there. Y'all just don't know about it. Okay. Personal BYOD and ransomware protection using containers and so forth and so on. And that I can, if somebody wants me to go through the talk on how you do that, I can explain it and so forth. But where I want to go is this other open source initiative, which is, it's called PDS, Personal Data Storage. And it was started by a guy named Pentland at MIT Media Lab, who some of y'all may know. And his idea was, he shares my view of privacy, my view of this is your stuff, you should be able to control access to it. And he came up with this idea that you put all of your personal data, on a device, whatever, okay? And there's a agent inside of that device that controls access to your personal data. But it controls it in an interesting way. It controls it by you allowing a person to ask questions of you, but it doesn't show them the raw data. There's no access to the raw data unless you, the owner, explicitly allow certain pieces of the raw data to get out for a certain agent out there. Like if it's a new doctor you've got, you can give him access to some of the raw data and answer some other questions he wants answered. So the classic example of this kind of concept is you're in a bar and you raise your phone up. The bar queries, it's a real bar, okay? And your phone says, yes, he's over 21. It doesn't say your birthday, which is what your driver's license says. Okay? So that's the classic example. So to tell everybody, at MIT, on the Kerberos Consortium page, and there's a reference to all this, is full open source for PDS, for implementing PDS. And it's of a sort, and remember who I am, it's of a sort that I could put it in a drive, particularly an SSD. Okay. So originally Finland started this PDS as a cloud initiative. It failed because people didn't trust that kind of data to be on the cloud. So he couldn't get people to actually want to do it. And so now he switched to putting it in devices. And so now they're directing their activity to have a personally maintained device. So this is a self-encrypting. So all Western Digital, $100 USB drives. Western Digital is has the largest market share in the world of USB drives by far. 100% of them are hardware self-encrypting. And this password you set is the key encryption key for the media encryption key. So this is a brick right now, and you can buy it at Staples. And they have about a 40% global market share. So don't tell me self-encrypting drives are not successful. Don't tell me nobody can ever understand them. Okay, it's not true. So anyway, so you go to Media Lab, you can get Open PDS, download it. You can see all of their motivations. You'll see that they're completely congruent with ours. Okay, and it gives you a way to do this. The second thing, how many of y'all have heard of homomorphic encryption? Good. So 6 or 8 years ago, I said what most everybody said about homomorphic encryption, which is great idea. How many years do you want to compute to do, a 3-line program in C using homomorphic encryption? Because it's this intractable, it's provably doable. The computation is impossible. You just can't do it. Okay, it's just impractical under any circumstances. So what homomorphic encryption does is it's a really, really simple concept, but it's so simple and so crazy, it's really hard to get your head around it. So the idea of it is, and it was really Ron Rivas at the RRSA at MIT that originally suggested the idea in the 80s. The idea is you do operations on encrypted data, and the encrypted data is never decrypted. And the operations themselves are encrypted. Yes, the operations themselves. And so it's one encryption operation of request for data going to an encrypted data, and it comes back with an encrypted result, which is correct using the key that you already have. And so on the storage device, the plain text never can be seen, and the requests for information to the thing can never be interpreted over the line. And you don't, and over the line, you can never see the meaning of the responses. Crazy, crazy idea. It can be done. In the general computing case, it can be done. It's been proven it can be done. That particular technique is impossible. So we had a breakthrough in the last 4 years, and it was partly MIT, but it resulted, so MIT has a open source, it's called CryptDB. It is a full homomorphic encryption system for full SQL. So you can build a SQL database inside of this guy with all the homomorphic properties. So the request that's made to the database is completely encrypted. Nobody can figure out what it is. The response is completely encrypted. Nobody can figure out what the database said back. And the database itself is fully encrypted. Crazy stuff, okay? So the question was, what was the solution to the problem? How did they, oh, by the way, CryptDB, instead of taking 100 years to compute, 6 SQL queries, okay, it's 16% slower than plain text SQL. So this is a huge, now all of a sudden we've conquered the, how do we make it go fast? So the overhead is 16%, which my argument is not much. There's not much overhead now to do full homomorphic encryption. And so so part of the model, it actually ties in directly with the PDS stuff, uses something called OAuth to allow people to make the queries of the system. So the PDS stuff uses, how do I allow you to ask me a question of my stuff? And so it uses OAuth, which is all over the web. OAuth is the single sign-on that you see from Google and every place else. Okay. And so the whole idea is you can create personal data, and you can grant access to somebody to an answer to your personal data. Okay. Without anybody else knowing either what the request was, what the answer was, or any access to the data at all on that device. This is insane. So here's some examples. So what they did was they did divide and conquer. It's a really simple idea. They noticed that for any given compute operation, so SQL is just a collection of basic primitive operations. Okay. What you do is you create a full homographic solution for that one little operation. So SQL might be 40 or 50 of these primitive operations. And so what you do is you encrypt everything using an encryption algorithm that's suited to that one operation. So storage guys should love this. This means that what CryptDB does is CryptDB takes your database, your data, replicates it 40 times, encrypts it with a different encryption algorithm for each of the 40 times. And each encryption algorithm is associated with one particular type of operation. And now all of a sudden it goes fast, because it turns out once you decompose the operations and you're smart about how you do it, you can now, the homomorphic is really fast because it's suited to only that one thing. So here are 3 examples. One is search. You basically say, is this Alice? And Alice is encrypted as such and such. Bob is encrypted as such and such. Eve is encrypted as such and such. And so what happens is you send to this thing the encrypted version of Alice, which is the request. Okay. This thing has the database, which is the encrypted version of Alice, Bob, and Eve. Okay. And it just matches the encrypted version to the encrypted version and responds with yes or no, and you can encrypt that too. Okay. And it is Alice in your database, and you got it. So search is like really, really easy. Okay. Addition is really simple. There's the old RSA exponentiation thing. So 2 plus 3 equals 5. What does 2 plus 3 equal? The answer is 5. Well, you take the b to the exponent of 2, b to the exponent of 3, and multiply the two, don't add them, and you get the added result. And so b to the 5th power is the addition of 2 plus 3, and that gives you 5. So this is a case of how do you solve homomorphic for addition. And what I want to say, just to be clear, is trust me, guys, there's a lot of technical work on this stuff now. So I'm giving you the surface of understanding how this thing works and the opportunity for storage guys, because now the 1 gigabyte database, SQL database that you got sitting there turns into a 40 gigabyte thing that can be highly parallelized for completely secret search. Insane stuff. Okay. Multiplication is just, it's you multiply times two values. So 2 times 3 is it gets encrypted to 2a times 3b. That's equal to 6ab, and you divide by ab, and you get the answer to the multiplication. So 2 times 3 is equal to 6. And there's the homomorphic solution for multiplication. It's insane. Now, what is actually done in like CryptDB is the encryption is much more sophisticated, but those are the fundamental operations that yield the values. So SP-SED rule number 2, and I'm available for consulting if anybody wants to know how to do this one, is you put a payment system on top of your PDS system that's sitting inside of the drive, a micropayment system. So you go to the bar, and the bar guy can get, if he pays your system a penny, he can get whether you're over 21. But the more important one is if you go to your employer is already paying for all this data on you. And you say, I'll give you answers to these questions. It'll be $1.50, thank you very much, or $50. Okay. Now, with a billion of these devices out there, okay, actually in the case of phones, we got a lot more. If I can make money off of my device, I'm a poor slob, and now I've got a way to bring my own data into a thing, whether I'm a company or a person or whatever. I can bring my own data in here, and now I charge you for access to that data. So Google actually has to pay, right, some money, okay, out of their little reservoir of money. They give me a little share, and now all of a sudden I've tickled the greed drug, okay, of everybody on the face of the planet. Okay, this gets really interesting fast. Okay, so this is sort of like the next Facebook. Okay, and I'm not going to do it. I'm too old. I'm going to die. Okay, so y'all can go off and do it. I got so many patents you won't even believe it. And so my thing is, but go off and have fun with this. This is just a cool idea, and it's a lot of fun. And by the way, I wrote the core spec. I will tell you, I wrote the core spec with this in mind. So it can implement a payment system, okay, among other things, okay. And so I actually knew about this. So now I'm out of time, and this is the last slide. The challenge is to you. The core was designed to provide services that are essentially, all this stuff. No kidding. I did this stuff at Seagate. I know what can be put in rotating media. I've been working with SSDs, you saw with the Micron thing, for years. No kidding. We can put this stuff in these things. Okay, no kidding. Okay. And the trick is make it possible for everybody on the face of the earth to make money. And then all of a sudden you'll solve the hardest problem, which is people bringing their personal data back to themselves, which is an interesting question. How do you get them to bring their stuff back to themselves? And now all of a sudden, because they can make money, not because they think it's neat technology. That's the end of my talk. Does anybody have a question?
So if people want to learn more about this and the way how you presented it, is it done in books or white papers or?
So at the end, the last slide, and it's, I should have shown it to you, is a list of all the references. And so what I did was I picked off what I call root references for everything. So if you go to those references, you can go off into the web. And those are the really good, those are the papers that I think are the ones that are the best. So for example, PDS, I give you access to exact, I give you the path to the exact PDS explanation. It's really hard to find on MIT. And I give you the path. And for the homomorphic, I give you a IEEE spectrum paper, which is a great paper to start with, and so forth and so on. Yeah.
Just trying to stimulate some other questions from the audience. But in Europe, the data privacy regulations, the regulators in analyzing what's the value of one's personal data, they come up with some estimate that's like the low hundreds. And this is the type of value that like the large media is extracted for free. And if this was to go forward, do you think that that's sort of the right range of value of a person?
No, I think once you get people to be able to make money off their own data, and you make it available to everybody on the face of the planet, this is what I was doing with the self-encrypting drives, is make this stuff available to everybody on the planet. Then what you'll find out is that the number of things that people will invent that they want to protect far exceeds what these governments are looking at and identifying. Okay, and people will protect crazy things like I've been doing drone experimentation for 5 years, and I've got all my little drone experiments, and I'm going to protect it, and you want to know my little drone experiment results. I'll show you what they are, but you're going to owe me some money. Or answer questions about what I've learned. Any other questions? Yeah. Okay, so the last line of that slide, I said, I can talk to you about that, okay, but it would take me another presentation. So there is a way to do it, but it's, so the resilient systems, the use of ranges on these drives, that's the real trick, because when you're on the internet or doing whatever you do. So what the government did was they have 4 OSs, all real OSs on the drive, okay? And actually what happens is it can bop off to another OS and use a different range. So ransomware protection is things like that range is the OS that's running when you're, on the web and stuff is just not the OS that's going to run when it goes to your corporate data, that kind of thing. And the partitions. Remember, the biggest attack is partition table attack. And so the bad guy can only see the partitions that the range permits him to see, which is crazy. Okay? So he doesn't even know about the other stuff. He has no way to get to it or anything. So it just goes, it's the same divide and conquer type strategy.